Hello and welcome to this FloEFD example where we're going to be looking at a cyclonic separator in FloEFD where we have a air inlet, we have two outlets for the cleaning stages and the third clean air outlet. This is a passive device using vortex technology, and let's have a look at some of the design behind this particular separator. So you can see that we have a single spiral that's going to be forcing air towards the outside of this vortex tube, and we can understand that the particles are going to be flung outwards and then separated from the flow as it goes through the device. So in FloEFD we can check the geometry to ensure that we are getting the correct fluid region in the model, so the air cavity or the air volume is going to be correct, and you can see on the screen this blue volume, which is the correct air volume, so we're ready to go. So let's go to our FloEFD analysis and look at some of the setup. So here, first of all, we have 100 CFM on the inlet. We then have 3 pressure outlets, the first stage of cleaning, the second stage of cleaning, and then hopefully the last clean air stage right at the bottom. So let's load the results. So first of all, let's take a cross section. We have that there, and we can have a look at what the computational mesh looks like. FloEFD uses a finite volume mesh, and you can see we have coarse regions on the inlet, medium regions around the spiral, and then we have a very fine grid region in red there on the outlet of each one of the vortex tubes, which indicates our separation zone as the particles are sticking to the outside of the vortex tubes. So that's what the computational mesh looks like. Let's have a look at the velocity through our model, and I can probe that now and get a feel for what sort of velocities I'm going to be getting through the model. Right, so we can see there velocities, and on the outlet as well I can see what sort of velocity that I'm going to be getting. We can also have a look at what the flow pressure looks like. So to maintain that 100 CFM, what's the delta P got to be? Well, we can see the inlet pressure and the outlet pressure, so maybe 0.18 psi or so pressure, upstream pressure required to maintain that 100 CFM through the unit. We can introduce and look at some zero mass particles into the flow just to visualize what the airflow looks like. So you can see there we can actually play these, bring back the housing, turn off the section, and you can see what the flow trajectories look like as it goes through the model. I can take this section like this and we can see the flow with these zero mass particles. Okay, but because we want to understand what the separation efficiency actually looks like, then to do that we can actually use something called a particle study. So let's activate this particular particle study. Now I've got 3 injections. I've got 50 micron, 5 and a 0.5 micron injection into this model. If I just edit this, you can see that this is going to be a 50 micrometer, 100 injections, and I've got a plywood material on here at 50 micrometers, and we want to understand, or micron, what the flow looks like. So let's just activate this, and if we show that now, right, so we can see the particles coming in to our model. This is colored by velocity. You can see there is the swirling effect as it goes down. You can see how they're sticking to the outside of these vortex tubes. There's no moving parts in this, completely passive device, and then you can see how it's being separated and moved out and then going out towards the outlet of the first stage. A little bit gets through to the second stage, but not as much as the first stage. So this is the separation efficiency is pretty good for 50 micron. Let's have a look at what happens at 5 micron. Alright, so we're getting a little bit more. So the first stage is taking care of most of it, but the second stage a little bit more getting through this time, and then finally a little bit more getting through out towards the outlet as well. And then finally let's have a look at 0.5 microns. What does that do? Well, we get a lot of separation in the first stage, A lot more going through to the second stage, but the last stage, there simply isn't enough mass in those particles, so the separation isn't as great for these 0.5 micron particles going through our separator. So we can get actually a feel for exactly how good the separation efficiency is. So the way to visualize that is to use surface parameters. So if we look at our stage 1 and actually show that looks like. So in the stage 1 we're removing 50 micron, removing 98.5%, 5 micron 93%, but in the 0.5 micron we're only moving 32.4% of those particles out of 1,000. And then finally, if we look on the outlet to understand how many particles are going down there, then we can see that the 0.5 micron, only 0.1% of the 50 microns are getting through, but the 0.5 micron, you can see 462 of the original 1,000 particles are getting through. So only a 53% separation efficiency at 0.5 micron. Finally, let's see what sort of erosion rate we're going to be getting on our spirals to see how many particles are actually hitting those surfaces. And if I hide the geometry, we can now see, due to the top section there, you can see what sort of erosion rate. The outer ones aren't getting as much as the inner ones, but that shows you which particles are hitting on which surfaces and where, and how badly the wearing effect is going to be due to the particles going through this particular system. So this was an example of FloEFD separation. Thank you very much for your interest. Goodbye.